Determining the correct feeder size involves several factors, and while parallel 500 kcmil conductors might be appropriate, it's crucial to verify this based on the load calculations and the distance to the service panel. Let's delve into the considerations for feeder sizing and service pipe requirements. Firstly, the feeder size must be adequate to carry the calculated load. This involves determining the total amperage draw of all connected devices and appliances. The National Electrical Code, or NEC, provides guidelines for calculating these loads. It's essential to consider both the continuous and non-continuous loads. Continuous loads are those that operate for 3 hours or more at a time, and they require special consideration when sizing conductors. The NEC requires that conductors be sized to carry 125% of the continuous load. Secondly, voltage drop must be considered. Over long distances, the voltage at the load can be significantly lower than the voltage at the source due to conductor impedance. This voltage drop can negatively affect the performance of equipment and appliances. To minimize voltage drop, it may be necessary to increase the size of the conductors. The NEC provides recommendations for maximum voltage drop. A common recommendation is to limit voltage drop to 3% in the feeder and branch circuit combined and 5% overall. Thirdly, the ampacity of the conductors must be sufficient to carry the calculated load, including the 125% requirement for continuous loads. Ampacity refers to the current carrying capacity of a conductor. The NEC provides tables that list the ampacity of various conductor sizes and types. These tables take into account the conductor material, insulation type, and ambient temperature. It's important to select conductors with an ampacity that is equal to or greater than the calculated load. Fourthly, the insulation method and ambient temperature affect the ampacity of conductors. When conductors are installed in conduit or cable trays, they may not be able to dissipate heat as effectively. This can reduce their ampacity. The NEC provides correction factors for adjusting ampacity based on installation method and ambient temperature. Fifthly, conductor material is a factor. Copper and aluminum are the most common conductor materials. Copper has a higher conductivity than aluminum, which means that it can carry more current for a given size. However, aluminum is less expensive than copper. The NEC provides different ampacity tables for copper and aluminum conductors. Now let's talk about the number of service pipes. As a general guideline, the number of service pipes depends on the size of the service entrance. For a 400 amp service, one 4-inch PVC pipe is typically sufficient. For larger services, such as 600 amp or 800 amp, 2 4-inch PVC pipes might be necessary. The number of conductors permitted in a conduit is limited by the NEC to prevent overheating. This is known as conduit fill. The NEC specifies the maximum percentage of the conduit cross-sectional area that can be occupied by conductors. The percentage varies depending on the number of conductors in the conduit. For example, if there is only one conductor in the conduit, the maximum fill is 53%. If there are 2 conductors, the maximum fill is 31%. If there are 3 or more conductors, the maximum fill is 40%. To determine the number of conductors that can fit in a conduit, you need to know the diameter of the conductors and the inside diameter of the conduit. The NEC provides tables that list the dimensions of various conduit sizes and conductor types. Here is the process for determining the number of service pipes. Firstly, calculate the total number of conductors that will be installed in the service pipe. This includes the phase conductors, the neutral conductor, and the equipment grounding conductor. Secondly, determine the size of each conductor. This information is typically found on the conductor's insulation. Thirdly, use the NEC tables to determine the minimum conduit size required for the number and size of conductors. The NEC tables provide information on the maximum number of conductors of a given size that can be installed in a conduit of a particular size. Fourthly, consider the bending radius of the conduit. The NEC specifies the minimum bending radius for conduit to prevent damage to the conductors. The bending radius depends on the size of the conduit and the type of material. Fifthly, consider the location of the service pipe. If the service pipe is installed underground, it must be buried at a sufficient depth to protect it from damage. The NEC specifies the minimum burial depth for service pipes. Also, local electrical codes must be adhered to. Local electrical codes may have additional requirements for the number of service pipes. It's always best to consult with a licensed electrician to determine the specific requirements for the installation. The distance between the service head and the service panel can also affect the size of the feeder and the number of service pipes required. Over long distances, the voltage drop can be significant. To minimize voltage drop, it may be necessary to increase the size of the conductors. In some cases, it may also be necessary to install additional service pipes to reduce the distance that the conductors must travel. Here is an example. Suppose a service is being installed for a small commercial building. The building has a calculated load of 300 amps. The distance between the service head and the service panel is 100 feet. The local electrical code requires that the service pipe be buried at a depth of 24 inches. To determine the number of service pipes required, the following steps should be taken. Firstly, calculate the total number of conductors that will be installed in the service pipe. In this case, there will be 3 phase conductors, 1 neutral conductor, and 1 equipment grounding conductor for a total of 5 conductors. Secondly, determine the size of each conductor. Based on the calculated load of 300 amps, the phase conductors should be 3/0 American wire gauge, or AUG, copper conductors. The neutral conductor should be sized according to the NEC. In this case, the neutral conductor should be 1/0 AWG copper. The equipment grounding conductor should be sized according to the NEC. In this case, the equipment grounding conductor should be number 4 AWG copper. Thirdly, use the NEC tables to determine the minimum conduit size required for the number and size of conductors. Based on the NEC tables, the minimum conduit size required for 3/0 AWG copper conductors, 1/0 AWG copper conductor, and 1 number 4 AWG copper conductor is 2 inches. Fourthly, consider the bending radius of the conduit. The NEC specifies the minimum bending radius for 2-inch PVC conduit. Fifthly, consider the location of the service pipe. The local electrical code requires that the service pipe be buried at a depth of 24 inches. In this case, 1 2-inch PVC conduit will be sufficient to accommodate the conductors and meet the requirements of the NEC and the local electrical code. However, it's important to note that this is just an example. The specific requirements for each installation will vary depending on the load, the distance, the local electrical code, and other factors. It's always best to consult with a licensed electrician to determine the specific requirements for the installation. When considering parallel conductors, each parallel conductor must be the same length, conductor material, be the same size in circular mil area, and have the same insulation type. Also, all parallel sets of conductors must be run in the same raceway. When using parallel sets, be sure to divide the total ampacity needed equally among the parallel sets. For example, if 600 amps are needed for service and 2 sets of parallel conductors are used, each parallel set needs to be rated for at least 300 amps. Also, remember that equipment grounding conductors are always required, and you should verify local requirements for the service disconnect.